Right. So guys, today we'll be solving A, B, C, D, E. So let's start with discussion of problem A. What does problem A say? Problem A says that you are given an array A of n integers. Then the definition of median is given. You are allowed to choose an integer I and increase AI by 1. Your task is to find the minimum number of operations to increase the median of the array, right? So guys, this is problem A. And what does it say? We are given an array of n integers. Okay. And what kind of operations can we do? In one operation, we can select an index I and increase AI by 1. Okay. Increase AI by 1. What do we need to find? We need to find minimum moves to change the median. Okay. This is what we are told to do. Now, guys, let's take some examples and try to understand what this problem means. First of all, what is a median? A median is an element that is at the middle of the array after we sort it. Okay. Now, what does this mean? Let's say our array is 1, 5, 3, 2, 4. If we sort it, our array becomes 1, 2, 3, 4, 5. Now, if you look at this array, the middle element is 3, and hence 3 right here is the median. Okay. Now, let's say it was not 1, 5, 3, 2, 4. It was just 1, 5, 3, 2. Okay. So if we sort the array, it's 1, 2, 3, 5. And the median in this case, it is given that it should be the ceil value of n by 2. Right. So in this case, just a second. Right. So in this case, I think it is 2, right? That is what is defined. 2, 3, 8, 9. Yeah. So the index will be 2. Now, what is the main observation here? The main observation is that we are only increasing elements. Put a yes in the chat if you have understood the problem. Okay. Have you guys understood the problem? Chore says yes. Ayush says yes. Okay. Now the problem says that we can only increase the values. So tell me guys, in this particular array, if the elements are 1, 2, 3, 5, can the new median be smaller than 2 or smaller than current median? Tell me guys. Why? Because let's say our median is smaller than the current median, then it means that it is from one of these elements, right? But to get these elements over here, we have to make them 2. Otherwise, how will it come in this position? Because let's say it is 1, 1, 2, 2, 3, and then you're 4, 4, 4, 4. Okay. The median right here is 3, right? If I want to, let's say, bring this 1 over here, can you see if I make this 1 into a 2, the array just becomes 1, 2, 2, 2, 3, 4, 4, 4, 4. It is still over here. Only when I make it into a 3, the array becomes 1, 2, 3, 3, 4, 4, 4, 4. And now when I increase this to a 4, the array becomes 1, 2, 2, 3, 4, 4, 4, 4, 4. So when did the element that we wanted to bring to the median become the median? Is when it is larger than the current median. Do you guys understand this? That we can only increase the median. Okay. Now, since we are told that we want to increase the median, right? And we want min number of moves. The first observation is we can only increase median. And the second observation is that we want min number of moves. Okay. So can you guys see that if I want min moves, then my new median is going to be nothing but my current median plus 1. Do you guys see this? Yes. For example, if my sorted array is 1, 2, let's say 3, 3, 4. Okay. In this case, my current median is 3. The new median which I'm aiming for is just 4. Now, my task is I have to make the median of this array 4. Right? This is Ruchit says, please repeat after min moves. Okay. Ruchit, what I'm trying to say is we, we are trying to minimize the number of moves and the median can only increase. So let's say my current median is 3. We can only increase the median and we want min number of moves. Do you see that making the new median 4 is going to be the most optimal because we are increasing the median by only 1 and that hence is going to cost the least number of moves, right? Because let's say we wanted to make the median 5. So first I would make it 4, then I would make it 5. Does it make sense? Right. Now, so we've got this that my new median is going to be current median plus 1, right? And after that, we also know that we know what the median is. So here, if I add 1 over here, because I know my median needs to be 4. So I add 1 here. My array now in sorted order becomes 1, 2, 3, 4, 4. Is my median still 4? Tell me, guys. Is my median 4? No. Now I will take this. I will add 1 again. And my array became 1, 2, 4, 4, 4. Is my median now 4, guys? Tell me. Okay. So it took us 2 moves to do this. Let's take one more example. And I think now it should be clear what the answer should be, right? Let's say my array is 3, 3, 3, 3, 3. So my median is 3. And now we have to make our median 4. So I change this 3 into a 4. My array becomes 3, 3, 3, 3, 4. I change my array, change my current median to a 4. So my array becomes 3, 3, 3, 4, 4. And now I change my element to this to 4. So my array becomes 3, 4, 4, 4. Right? So it took me 3 moves. Now tell me one thing, guys. If I added a 5 here, would the answer change? Or would the number of moves still be the same? Tell me, would it change or would it still be the same? Right? So a thing to notice is that you know the median and you know to its right how many elements are the same. Can you see that you have to make all these elements equal to 4? Only then will the median be 4. Because when you make this 4, these elements will be shifted here. Then you make this particular 4, and then this elements get shifted here. And then last but not the least, you make the last element 4 as well. Does it make sense, guys? You know what the median is, and you know to its right how many elements are the same. Now, If I make this 3, this 3 goes over here and these 3s get shifted. Now, from these 3, I make this into a 4. And last but not the least, this is 1, 3 remaining. So I make it into a 4. And if there was some elements, 5, 6, whatever, it wouldn't really have mattered. So what is the solution here? The solution is just count of elements equal to the median to its right, or you can say greater than equal to its current index, right? Greater than equal to current index. Is this idea clear for everyone? Tell me, guys, is this idea clear for everyone? Let me take, is there anyone for whom this idea is not clear? Clear for everyone? Great. So now let's look at the code, right? So I'll just show you the code. Just 1 second. Right. So it is very simple that I have my current, I'm taking an input. Now, this is how you take input for an array. I sort the array. And after that, what index is my median on? It is on n plus 1 by 2 minus 1. Now, why is this so? If you can see, if my index is 5, 5 plus 1 by 2 is 3. And since we are working in zero-based indexing, right? Let's take an example, right? Yeah, basically seal. I'll teach you a new thing right now. For people who have not yet joined TLE Eliminators, such tricks are taught very well here. What is this trick? If you want to compute seal of A by B, okay, this function, there is a formula for it. What is the formula? It is just A plus B minus 1 divided by B. This is the formula for seal of A divided by B. This is exactly what I'm doing here. I wanted to compute seal of n by 2. So I'm just doing n plus 1 by 2. And then I'm doing minus 1 because we are working in zero-based indexing. And after that, I just want to know how many indices are there that are greater than equal to I, and it is equal to the median. So I just run a while loop while j is smaller than n and ai is equal to aj, j plus plus. I could have also done count plus plus, and in the end, I just print j minus I, or basically the count of the elements. Is this implementation clear for everyone? Okay, someone says the formula again. So here is the formula. Seal of A by B is equal to A plus 1, A plus B minus 1 divided by B. For example, 5 divided by 2, seal, okay. Seal of 5 divided by 2 is nothing but 5 plus 2 minus 1 divided by 2. This is 6 divided by 2, which is 3, right? So seal of 5 divided by 2 is 3. And if you take something like 7 divided by 2, this is nothing but 7 plus 2 minus 1 divided by 2. This is 8 divided by 2, which is 4. Is this formula clear for everyone? Yeah, seal always gives an integer output, right? Seal always gives an integer output. That is how seal is defined, right? So this is all about problem A. Now let's move on to problem B. Someone says, please repeat that while loop. This is nothing but if my array is 1, 2, 3, 3, 3. So I need to count these elements here. So my I is right now here and my j is here. While my this element is equal to this element, I move this pointer ahead. Basically, this is I, this is j. So since these two are already equal, I move this ahead. Now, since these two are equal, I still move this side. And since these two are equal, I move this side. Now I come at the end of the array. How many elements are these? Let's say this is J, this is I, then this is just J minus I elements. You could have also done, you could just have counted using count plus plus, but I just derived the formula using these two indices, right? Let's say this is 1, 2, 3, 4. So 4 minus 1 is 3, and you can see that there are 3 elements equal to 3. Is this clear? Great. Now, let's move on to problem B. Problem B says you have an array of n integers. You can perform exactly k operations on it. In one operation, you can select any contiguous subarray of the array and insert the sum of this subarray anywhere. Your task is to find the maximum possible sum of the subarray after k such operations, right? So someone says it would be great if you can tell the expected rating. Uh, I am not that quite good at telling you the expected rating, but there's a bot known as TLE bot. I will share the expected rating of each problem after this PCD, right? Great. So what does this problem say? The problem says that, okay, for problem B, the problem says that we are given an array of n integers and we can do k operations. Okay. Now, what does now in each operation, what exactly can we do? We take the array, okay, we are given an array of n integers. We take any subarray. Does everyone know what a subarray is? Subarray is a continuous chunk of the array, right? Continuous chunk of array, right? We can take any continuous chunk of the array. After that, whatever the sum this array has, this subarray has, right? Let's say it is S. We can insert S anywhere inside the array. For example, my current array is 1, 2, 3, 4, 5. Let's say I take the subarray 2, 3. The sum of this is 5, right? So I can insert this 5 anywhere. Let's say I insert it in the second position. So now my array is 2, 3, 4, 5. This is one operation and we have to do exactly k operations. And we are also allowed to choose an empty subarray. Is this much clear, guys? Tell me. The problem says that we are given an array of n integers on each, and we have to do exactly k operations, right? In each operation, what do? We choose a subarray. It can be an empty subarray as well. Then whatever the sum it is, we can insert it into the array, right? So in the end, what do we have to print? We have to print the sum of the array, and we would like this to be as large as possible. Okay. And this answer can be really large. So we have to print it modulo 1 in 9 plus 7. Okay. Now, guys, this is very instructive problem. It is a standard kind of problem, but with a great twist on it, right? So what do we initially need to find? Let's say for the first operation, what would be best for us? Let's say our array is -1, 1, 2, 3, -9, 1, and -10. Okay. Can you see that if I wanted to do, if I wanted to add only, if I wanted to do only one operation, then what would I do? I would pick the subarray with the largest sum and I would just insert it anywhere into the array. Does it make sense, guys? Now, what does subarray with the largest sum mean? It means that over all the subarrays of the array, right? This subarray has the largest sum. For example, you can see that this array has sum 6 and no other subarray in this array has sum 6. You can check it out, right? So if we only had one operation, what would I do? I would just take this 6 and I would insert it anywhere, right? Minus 1, 1, 2, 3, minus 9, 1, minus 10, and I'm allowed to put 6 anywhere. Okay. Now let's say I wanted to do this again, but I have not inserted 6 yet, right? If I have not inserted 6 yet, can you see that this is still the largest subarray sum? Tell me, guys. Is everyone clear with this? If I have not inserted the 6 yet, the largest subarray sum remains the same. So can you see that if I just put the 6 here, this is my largest subarray sum now because this is greater than equal to 0. Tell me, guys. And what is this? This is the sum of the largest subarray, sum of largest subarray of original array, right? Original array, right? Now, tell me, guys, okay? In the first operation, I increased by sum by 1 into whatever the subarray sum was. Now, if I do this again, this is 1 times sum of subarray plus 1 times sum of subarray. The sum will now increase by 2 into sum of largest subarray. Do you guys agree on this? First, in this operation, the sum increased by 1. Now, if I do this again, the sum will increase by 2 times the original subarray sum. So basically, the sum of this is 12, right? The sum was 6. Now the sum is 12. Okay. Now, if I do this again, okay, let's take a smaller example. Okay, let me take a smaller example and make it much more clear. Let's say the array consists of only one element, okay, which is 7. Do you guys agree that the largest subarray sum is 7 itself here? Tell me, guys. Yes. So in the next move, the array becomes 7, 7. Okay. And now my largest subarray sum is 7, 7. Do you guys agree? Yes. Now my subarray sum is the largest subarray sum is 7, 7, which is 14. So my array becomes 7, 7, and I put 14 here. But I'm not putting 14 here. I'm putting this. I'm putting this array itself. Okay. So 7 and 7. Right? Do you guys agree that this was 7? Now this became 14. Now this became 28. Right? And if I do this again, this becomes 7, 7, 7, 7, 7, 7, 7, 7. Basically 56. Do you guys agree? Tell me, guys. Yes? So the basic observation here is that the sum increased by 7, the sum increased by 2 into 7, the sum increased by 4 into 7. So basically, whatever the largest subarray sum was, right, on every move that you do, the sum that you can increase doubles and that you can add to your answer. Does it make sense, guys? Tell me. Right? So basically, what is our solution? Our solution is that you find the largest subarray sum or the most positive subarray sum. Okay. Let's say my current answer. Okay. What is my final answer? My final answer is the sum of the array, right? So my current answer is just sum of array, right? Now, after this, I wanted to do one move. When we did one move, can you guys notice that my sum increased by whatever the largest subarray sum was, right? So when I do one move, my answer increases by whatever the largest subarray sum was. Do you guys agree upon this? Yes. Now, for this particular array, do you guys, Achilles says, can you repeat this point? Yes. So let me just tell you. Let me just recap, okay? It got a bit messy. Let me just recap. So we are expected to find the largest sum of array. For this, what did we notice? We noticed that if we wanted to do only one move, we can just find subarray with largest sum. Okay. Now, let's say we found the subarray with the largest sum. Let's say it is minus 10, 1, 2, 3, and minus 10, right? Now, we can put the sum of this subarray next to itself only, right? That will be the most optimal. It is a greedy kind of strategy. Like whatever this was, I will just put it next to it. Does this make sense? Okay. Now, after putting it next to it, I'm not putting 6 next to it. I'm putting 1, 2, 3. So minus 10, 1, 2, 3, 1, 2, 3, minus 10. So do you guys see that the sum of the subarray doubled? Do you guys notice this? Right? So for this particular array, what is the subarray, largest subarray sum? Let's say the largest subarray sum here was S. Can you see here it became 2S? Right? Didn't it become 2S, guys? Tell me. Yes? So this is all that what we are going to simulate. Now let me show you how we are going to simulate. We need to print the sum. Okay? Sum of the array. Let's say my array is initially 1. So, and my sum variable, okay, it is initially the sum of the array. Okay. Now, you do one operation. The array becomes 7, 7. And here the largest subarray sum, I'm representing it as LSS, okay. The largest subarray sum, it is 7. Do you guys agree that the sum increased by whatever the largest subarray sum was for this array? Tell me. Yes. So sum increased by 7. So sum became 14. And what is the largest subarray sum here? It is 7 into 2. So my largest subarray sum here is 14. Right? Let me put a minus 1 here so that, no, let me not put it. But keep in mind, these two are different things. Okay? It is not necessary that the sum and the largest subarray sum is the same. Now, if I do this again, my array becomes 7, 7, 7, 7. Can you notice that the sum increased by 14? Yes. Did the sum increase by 14 or no? So my sum became 28 and my largest subarray sum is just the double of this. So it is 28 now. So what do you guys notice? When I do an operation, the sum increases by what the largest subarray sum was. Okay. And my largest subarray sum doubles. Do you guys notice this? Right. So this is all that you need to do. Right. And in the end, we have to use modular arithmetic, right? So there are some modular arithmetic formulas. If you are not aware of them, you can check out our courses. It's there. But in general, the thing is there is no negative used here. What many of you guys faced an issue with is the minus one. So the thing here is there is no minus one here, right? There is no minus one. Like there is, I will tell you how. Now, the thing here is that the the current sum of the array can be negative, right? It can be negative. So, what is the mod of negative numbers? This is a big question. What is the mod of x when x is negative? Okay. First of all, do you guys agree that yes, I can explain the modulo part in detail. That let's say my modulo is p, x is nothing but x modulo p when we have to take it under modulo, right? Do you guys agree upon this? Okay. If I have to take a number under modulo, so it is just this. Now the thing is, this is negative. For example, let's say x is minus 5 and p is, let's say, 2. So minus 5 modulo 2 will give me 1, right? Because remainder is minus 1. Okay. Yes. Now, the simple thing here is that there is a formula for it. What is the formula? It is nothing but, let's say, this x is smaller than p. Okay. Basically, x modulo p. So for negative numbers, it is just x modulo p plus p, the whole modulo p. What is this? This is the formula for negative numbers. Why, guys? Why is this for negative numbers? First of all, this is a negative number, right? So we need to make it positive. And one thing to notice is that x modulo p is same as x plus p modulo p, because x and x plus p are going to have the same mod, right? And since this is between 0 and p minus 1, okay, negative, when I add p to this whole value becomes greater than equal to 0. Do you guys understand this? This value right here, since this is negative, it is between minus 0 to minus p minus 1, right? If I add p to this value will become greater than equal to 0. So now, whatever this value is, which is greater than equal to 0, I just take it under mod. Does this make sense? Right? Paras says once more. Okay. So basically what I'm trying to say, yeah. So Achilles says, how does this guarantee answer would be same? This is basically the properties of modular arithmetic. It's like saying, how will x into 2 be same as x plus x, right? These are some formulas which you have to study, right? And one of these formulas is that if x is negative, then x modulo p, the formula for that is x modulo p plus p the whole modulo p. Because this is a negative number, and this negative number is between minus p minus 1 to 0. When we add p to this number in itself becomes greater than equal to 0. And for any number that is greater than equal to 0, I just take it under mod p and I have got x modulo p. Is this clear, guys? What I'm trying to say is x modulo p is same as x plus p modulo p. Yes. So that is all that we need to do. Accumulate function, what it does is it takes the sum of the array, right? So we take the sum of the array. After that, we mod it, then plus mod, and then the whole modulo mod. One thing that I forgot to discuss is that how will we take the largest subarray sum? Okay. How will we do this? So, yes, Raghav, thank you. So how will we take the largest subarray sum? There is a very standard algorithm for this. It is known as Cadence algorithm. If you have not already read it, you can check it out, right? There are a lot of resources online. You can just put what is Cadence algorithm. It is the way to find the largest subarray sum in O of n. Okay, this is the most efficient way. So I find the largest subarray sum. Okay, I'm storing it in answer. After that, this is the final answer that I'm going to print. Okay. Now I'm doing each operation one by one. What did we discuss, guys? We discussed that for every operation, what does happen? My sum increases by the largest subarray sum, and my largest subarray sum doubles. So that is all that I'm doing. My final answer increases by my largest subarray sum. It is the variable named answer. So final answer is nothing but final answer plus answer modulo mod. And my largest subarray sum doubles. So answer is equal to answer into 2 modulo mod. I do this k times because there are k operations. And in the end, I print final answer. Is this problem clear, guys? Tell me, what about others? Is this solution clear? TB says last part. Could you please specify what you didn't quite understand? Can you repeat Cadence algorithm? So the thing is, Cadence algorithm is a algorithm in itself. You will have to learn it, right? The basic idea is that whenever the current subarray sum becomes smaller than 0, you just set it to 0. I won't be covering that algorithm right here because it would take up a lot of time for building intuition and making all understand. Accumulate is just an inbuilt function which gives you the entire sum of the array. You could run a for loop as well. I'm just calling the accumulate function because I wanted to do this fast. Now, can you repeat what is final answer? Yes, you can do that as well. Shaurya, you can do that as well. Okay. Star says, can you repeat that loop part once? Sure. So here we discussed that let's say our current sum of the array is sum, right? And my longest subarray sum, we compute it somehow. So when I do one operation, my sum of the array increases by the largest subarray sum. Okay. This is the first thing that happens because this was 7. I added a 7. So my sum became 14. Right. So this is what is happening. My final answer increases by the largest subarray sum. What is the variable answer? It is the largest subarray sum. So my sum of the array increased by that. So that is why final answer increased by answer, and I'm taking it under modulo mod because we are expected to do that, right? And after that, for this particular array, can you see that my largest subarray sum, it was 7, now it became 14, it doubled. And for the next array here, it becomes 28. It doubles again. So whatever my current subarray sum was, my next subarray sum is just the double of the current subarray sum. So that is all that I'm doing k times. I just need to do what to do once and then I do it k times. Is this clear, guys? Yes? Amazing. Okay. So if this much is clear, let's move on to problem C. Right? What is problem?
Yeah, like in B part, like if case of 10 to power 9 range, then also we can do a GP sum, or like do we have to run a loop for that?
Yes, you can do it using a formula, but in this case, since k was small enough, you can just run a for loop and do this. There is a formula for it, but to not complicate it that much, I'm just using a for
Okay,
loop.
okay, fine.
Yeah. Right. Now, let's move on to problem C. Uh, okay. So, what is problem C, guys? You are given a tree with n vertices, and your task is to find the maximum number x such that it is possible to remove exactly k edges from this tree in such a way that the size of each connected component is at least x. Okay. What does the problem say? The problem says that you are given a tree. You are given a tree of n nodes, right? And you are given an integer k. What are we asked to find? You are asked to find the maximum x such that if you remove some k edges of your choice, okay? K edges of your choice, right? Then each remaining connected component has size greater than equal to x. For this particular problem, all that I am expecting is that you know how to implement a basic DFS and you know what trees are. Okay. This is what I'm expecting. If you don't know this, please pause. If you're watching it live stream, right? Learn these topics and then try to do this problem or get back to the PCP, right? Because these two problems are very important. These two topics are very important. Okay. So instead of finding the max x, let's find if some possible x is there or not, right? You can still watch, right? I'm going to teach it in such a way that the solution, not the code, but the solution is clear whether or not you know the problem or not, right? Now, let's take this tree, okay? 1, 3, 5, 2, 4. 1, 3, 2, and 5, 4. Here we are told that we need to remove one edge. Okay. K is equal to 1. Now I have to remove one edge, right? Let me see which edges I have to remove. If I remove this particular edge, the array becomes, the tree becomes 1, 2, and it becomes 3, 4, 5. Here you can see that each connected component, what is a connected component? This set of vertices are connected. This set of vertices are connected. So this is called a connected component. This is called a connected component. The size of this connected component is 3. The size of this connected component is 2. Since each element, each connected component has size greater than equal to 2, for this case, the answer would be 2. Similarly, let's say I removed this edge. Okay. If I removed this edge, you can see that my array is something like this. My tree is something like this. The size of this is 1. The size of this is 4. If you can remove the minimum of these sizes is 1. So we can say that each connected component has size greater than equal to 1. So for this, after removing this edge, my answer is 1. I'll not do for all the other cases, right? Because it's more or less the same. The answer will be 1, 1. Can you see that the maximum possible answer that I can attain is 2? So can I say that the answer for this particular test case is 2? And if you see, the answer is 2 indeed. Is the problem clear, guys? Tell me. Yes? Now, if the Angus says no, what exactly is not clear? Did you try reading the problem once? Basically, we are told that we are given a tree and we have to remove K. Yeah, you have to disconnect an edge. Okay. Now you know the size of each connected component, right? The answer for removing that edge is just the min size of the of all over all connected components. This connected component size is 4. This connected component size is 1. So for this, the answer is 1. And if you remove this edge, the answer is 2. So what is the max answer possible? It is 2, right? So the answer for this test case is 2. Now the thing to notice here is, guys, if answer, I will be discussing it, Shaurya. So guys, tell me, if answer 2 is possible, what does this mean? This means that all connected components have size greater than equal to 2. Tell me, guys, this is what it means. If answer is 1, what does this mean? All connected components have size greater than equal to 1. Yes or no? Okay. Now, let's say 2 is my answer. Okay. My final answer, I'm going to teach you another topic today. In this contest, you're learning too many topics. It's just too much fun. So, answer 2 is possible. Can you say that answer 1 is also possible? Because if the answer is 2, all connected components have size greater than equal to 1. But is 3 possible? If my final answer is 2, what is expected from the judge is 2. Is 3 possible? No. Is 4 possible? No. Is 0 possible? Yes. So for one particular range, it is possible. And for one particular range, it is not possible. This right here, exactly, Kashish. This right here is what we call a predicate function. Okay, what does this mean? it means that it is false for some range, basically not possible for some range. And after a particular point, for all after it or before it, it becomes possible. Now, the thing to notice here is that you can binary search over this. Tell me, guys. Yes. If the answer is 2, 1 is possible, 0 is possible, but 3 and 4 are not possible. So, what is the idea here? We are going to binary search on answer. Okay. This right here is a topic in itself, right? Did you guys understand this much? Tell me this. Did you guys understand this much? Okay. In our particular problem, it is going to be true, 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 and then it is going to be false, 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 right? Now, I am. Shaurya says, how did you bring up intuition? The intuition is as follows, right? 2 is possible, then 1 is also possible, then 0 is also possible. But 3 and 4 are not possible, right? This is something that you observe instantly because it is a possible answer. Now, this is nothing but a predicate function, right? And if something is a predicate function, put this in your mind. You can binary search on it. Okay. So our function is of type something. Like let's say 2 is my answer, right? So 1 is possible, 0 is possible. Let's say 3 is my answer. So 2 is possible, 1 is possible, 0 is possible. But 4 is not possible, 5 is not possible, 6 is not possible, 7 is not possible. So we can binary search to find this particular T. And how do you binary search? Let's say you are on some element. Let's say you're on some element. If it is false, it means that you need to go to the left. And if it is true, you can store this value and then you can go to the right. Right. So what are we binary searching on? We are binary searching on max size. Right. Now, the thing is, we know this is binary search. Okay, I will show you with the code. Right. Okay. So we know it is binary search. Binary search is this much only. Okay. Left is 0, right is n, and answer is 0. If while left is smaller than right, this is my mid. If okay mid, then answer is mid, and then I go to the right. Otherwise, I go to the left, and in the end, I print answer. Is this much clear? Why it is binary search? Tell me, guys. Yeah. Now, if we know that this is binary search, all we need to focus is on writing the check function. Right? What do we need to do? We need to write the check function. Okay. Now, how do we write the check function? Let's say x is 2 and my tree is as it was given, right? All I need to do is a DFS call. This is a very standard kind of problem, right? I do a DFS call. Let's say I come here and then I come on this node. What is the size of this particular connected component? No, only this node. It is 1. Can I cut this edge? I can't, right? Otherwise, this will be 1. And I want x to be 2. Not possible. Tell me. Tell me, guys. Can I cut this edge? I cannot, right? No. Similarly, can I cut this edge? No. Great. So the size is 1. Now, the size of this connected component, what is this? Basically, what I'm trying to tell you is, what is the size of its subtree? Tell me, it is 3. Does this mean that I can cut here? Tell me. Yes. So I will increment my cuts by 1. Cuts plus plus. Okay. And now I need to find the subtree size of this, right? So if I find that this is 2, then great, I can do cuts plus plus. And in the end, the number of cuts that I make, if I can make k cuts, can I say that it is possible? For example, here I wanted to make 1 cut and I am making 1 cut. So it is possible, right? Yes. So this is what we need to find. And how do we find this? First of all, there is a technique to calculate calculate number of nodes in each subtree, right? What does that mean? It means that, let's say this is a tree, right? So how many nodes are in its subtree? We can calculate it. How do you calculate it? Let's say there are some children. First, I will calculate for this, then I will calculate for this, then I will calculate for this. So I go down. This is 1, this is 1. So, okay, I know the size of these subtrees. This is what? What is the size of each subtree? What is the size of this subtree? Plus 1, right? So this is 1 plus 1 plus 1. So this is 3. This will be 1 and this will be 1. What will be the size of this node subtree? It will be 3 plus 1 plus 1 plus this node. So it's going to be 6 nodes. Is this clear? Basically, if I know the subtree size of each node, I just add them and then I add 1 to it. So in my code, I will show you, okay? The current subtree size is 1 because I am on that particular node. Then I iterate over all the adjacent elements. And if it is not equal to the parent, basically I don't want to go to something that I have not visited once. I just add the size to whatever the size was. This function is basically returning the size of subtree of that particular node, right? Is this much clear? Tell me, guys. Yes?
हेलो
Okay.
सर।
Yes.
सर ये जो ब्रैकेट में एंड लिखा हुआ है इस फंक्शन को क्या बोलते हैं सर?
This?
यस सर।
Okay. Very good question. This is known as a lambda function, okay? It is
ठीक है।
not necessary that you do it like this. I basically
तो
in
वो पढ़ने के लिए पूछ रहा था कि नेक्स्ट टाइम पढ़ लूंगा ना, इससे क्या होता है फिर?
sure. These are basically just normal functions, okay? Like the one I would implement here. But during the contest, like if you think from my perspective, today I was trying to get to master, which I did maintain. I'll tell you after the contest, right? For me to write this function and to go up back again and write something and go down again, it takes a lot of time for me. So what do? I just write a lambda function, so I don't need to use my mouse. I can just write it in flow using my keyboard. So this is just a way of doing it. It's my personal preference. It is not necessary that you have to do this. It is something that I choose to do. Okay. So this is a DFS function, right? For every node, what do? Its current subtree size is 1. Then I iterate over all the adjacent nodes. If it is not equal to the parent, I just increment the number of subtree size of that child to its sz and then I return sz. Okay. Now don't care about this one. Okay. Now, while I am iterating, okay, let's say x is 2. This subtree size is 3, right? Since this is 3, can I say that I can cut this node? Cut this edge? Tell me. Yes, I can cut this edge, right? So if I can cut this edge, what I'm doing is cut plus plus. Okay. And then when I have to compute the subtree size of this node, this subtree should not be counted. So when I am on this node and I'm cutting this, what do I return? I return 0. Is this idea clear, guys? If I am making a cut, I do cut plus plus, and after that, when I want to return what is the size of the subtree of this node, it will be 0, because I made this cut and this connected component is going to be different than this connected component. Does it make sense? Okay. Now, one thing to notice is that while I'm doing this, this is 3, cuts will be plus plus. And when I'm doing this as well, so cuts will be plus plus as well, right? But the number of cuts I made was only 1. So what basically is happening is 1 extra cut is being counted. So I am just checking that cut has to be greater than k. This is the condition. Because initially cut should be greater than equal to k. But since 1 extra cut is being counted, I just remove this greater than equal to. Does this make sense? Because if my number of cuts is k plus 1, it means that the original cuts is k. So I can count on this. So this is all that I'm doing. This is my DFS function. If the size is greater than tree size is what I'm passing in mid, right? Then the size is 0 and then cuts plus plus. And in the end, I'm just returning cuts greater than k. If cuts is greater than k, it will return true. Otherwise, it will return false. Does this make sense, guys? Right? So this was a problem on binary search and DFS. Two types of topics combined, right? Binary search on answer and trees. Okay. So very nice kind of problem, right? Now,
Can you explain the DFS function again?
yeah. So basically, to compute the subtree size of each node, let's compute the subtree size of each children, right? Let's say this is 1. Basically the subtree size we know. Okay, this is 1, this is 3, this is 4. So what will be the subtree size of this node? It will be this node itself. So 1 plus subtree size of all its children, right? 1 plus 1 plus 3 plus 4, isn't it? If I take an example, let this be as it is. I'll just add 3 nodes here and I'll just add these nodes here. So isn't the subtree size of this indeed 9? Tell me.
Yeah.
Yeah. So that is what I'm computing here, right? SZ computes the subtree size of each node. After that, I have to make some cuts, right? Now, if the current size is greater than equal to the size that we need or mid, right? I say that I'm going to cut here. So whenever I cut here, I'm increasing the cuts that I make by 1. And if I make the cut here, do you agree that if I make the cut here, this subtree size won't be counted when I count this, when I count for this node subtree size? Tell me. Basically, if I make a cut here, can I say that this node is in this node subtree? There is no edge, right? So can I say that? I can't, right?
Yeah.
Basically, if this is the tree and I remove this edge, can I say that this node and this node are in the same connected component? No, right?
No.
So basically, when I'm returning something from here, I just return 0 if I'm cutting that particular edge. So if I am cutting that particular edge, I do cuts plus plus, and then I do SZ is equal to 0. Basically, stating that I've made a cut. So for its parent, I'm not going to count it in its connected component. That is all. And in the end, okay, I'm calling DFS 1, 1. Basically, I'm starting my DFS from the first node. Okay. And in the end, if my cuts is greater than k, I return true. Otherwise, I return false. Is this much clear now?
Yeah. Thank you.
Right.
Thank you.
Can you explain how that extra cut was coming? In my implementation, the extra cut was coming. Because when the size is greater than equal to the required size, I do cuts plus plus. So if the tree is like this and k is 2, for this subtree the size is 3, so cuts will be 1. I remove this edge. And now for this connected component, again, the size is greater than equal to 2. So I increase my number of cuts. But actually the number of cuts that I made is 1, right? Basically what I'm trying to say is if you had only this much and let's say size was x was 1. So here I'll make a cut, here I'll make a cut. And when I'm computing this, I'm making a cut again. So the number of cuts is 2, but I'm counting 3. So what you can do is in the end, you can do cuts minus minus. Or what I did is you can just do this cuts greater than k or cuts minus 1 greater than equal to k. So this is all about it, right? This is a problem on binary search. How does this DFS guarantee an optimal cutting for particular X? Okay, I can prove that to you. Okay. Let's say that X is 2. For this, we cannot make the cut. For this, we cannot make the cut. For this, we can make the cut. Okay. Now, here, if we don't make the cut, we are going up. Can you see that if I don't make the cut, whatever the subtree size or the connected component size is, it is going to be greater than whatever the connected component size of this node is? Tell me. So, what will be the maximum number of cuts I can make? That I want to find the smallest connected components that have greater than equal to x size, right? And I'm exactly doing that. Like, let's say I'm taking this example, okay? Let's say x here is, okay, this is the example that I want to take, right? This subtree size is 4, okay? Now, I decide not to make the cut here. Can you see that I am including this edge in this connected component if I don't choose to make the cut here? But it is not really required, right? It is not required. I can just take this connected component. X is 4 here, right? The required size is 4, Kuldeep. If you need size 2, yeah, okay. What if it is size 2? Okay, what if it is size 2? Let me tell you what happens if it is only size 2. Okay. If it is only size 2, if x is equal to 2, can you make this cut? Tell me, can you cut this edge? Can you cut this edge? Can you cut this edge? We explored all these cuts. Okay. Now we can only cut this. And this is the smallest subtree that we can cut that consists of these nodes. Do you get it? Like the smallest subtree that consists of these 3 nodes and that has size greater than equal to 2 is this, right? Because I cannot cut this individually. I cannot cut this individually. I cannot cut this individually. So I say, okay, I merge it with its parent. And now can I cut it? Yes. So I will cut it, right? Because if I don't cut it, I'm going to the top. But that is not optimal because I can already cut it. Then why not cut it? Does this make sense, Kuldeep? What is DFS 1, 1 doing? Yes, it is starting DFS from root, where 1 is the root. Basically, 1 is the root and its parent is also 1. Yes, it is greedy approach of cutting, you could say. It is always going to be optimal.
In this problem, we are finally calculating size, and while if size is greater than x, we are returning 0 to it, right?
Yes. That is all that we are doing. We are applying binary search. Now, if problem A, problem B, and problem C is okay, it doesn't matter, right? You can assume anything to be the root. The answer will, no, it won't affect. It won't affect the answer. I can share the proof to you via text, but this DFS function that I have written, it is a very standard problem. Okay. So if you root it anywhere, right, the answer is going to remain the same. Okay, it won't change. Just trust me on that part. I'll share the proof for it to you via Discord after this PC. Sure. Yeah, this problem of cutting the tree into connected components is a very standard problem. Okay, it's a very standard problem. It is not something that has come up right now. This DFS function right now, this is very common. Okay. Now, birthday gift. This problem is a bit messy, but I would love to explain, right? Like the way you think about it is not kind of natural, but if you understand the topic related to it, it will be very clean. Like, so what does the problem say? The problem says that we have to divide our subarray into some, we have to divide our array into some subarrays, okay? AL to AR1, AL2 to AR2, up to so on and so forth. And what do we have to make sure? We have to make sure that, let's say, for example, I'll just take this, right? So we have an array of size n. What do? We divide the array into some subarrays, okay, such that each element is taken in the subarray. We take the XOR of all elements in this array. Okay, we take the XOR of elements in this subarray. We take the XOR of elements in this subarray as well. What is XOR? XOR is a bitwise operator for people who don't know. The truth table is if you have 1 and if you have 1, you get 0. If you have 0, you have 1, you get 1. If you have 1 and you have 0, you get 1. If you have 0 and 0, you get 0. Basically, if the bits are not the same, you get 1. Otherwise, you get 0. Now, let's say this is A. Let's say this is B. Let's say this is C. Right? Now, what is the answer for this? It is A, bitwise OR with B, bitwise OR with C. This is bitwise OR. Don't confuse it with XOR. This is the bitwise OR. There are two operators, the XOR and the OR. What does the OR do? If there is at least one in the truth table, it is going to return 1. This is what the bitwise OR does. Okay. And this is what the bitwise XOR does. So the answer for this particular cut is just A or B or C. We have to make sure that whatever this is, right, as given in the problem, that all the XORs ka OR, basically the OR of each XOR of each subarray, it should be smaller than equal to X. Basically, let's say I cut the array into some parts and the XOR is X1, X2, X3, so on and so forth, up to Xk. Then X1 or X2 or X3 up to or Xk should be smaller than equal to capital X. This capital X is given to us, okay? Now, we have to print what is the maximum number K. Basically, what is the maximum number of subarrays I can split my array into such that this condition is satisfied. Does this make sense, guys? Shaurya says wasn't able to reach here. You can. If you are able to understand the question till now, feel free to continue. This is not an advanced topic. This is just mathematics. And this is actually easier than C if you know the idea. Because I solved it in C. Right? So is the problem statement clear? We are given an array. We have to split it into maximum number of subarrays. Let's say we split it into k subarrays. The condition that it should satisfy is x1 or x2 or x3, basically the OR of the XOR of all subarrays should be smaller than equal to x, where x is given to us. Is this much clear, guys? Tell me. Yes? Okay. Now, I want to teach you guys something, okay? I want to teach you guys a principle. How do you know? How to know if one number is larger than the other in binary? This is the first thing that I want you all to know. Binary, okay? For example, let's say my first is this and my second is this, okay? Which one of these is larger? This or X or Y? Y, right? Okay. 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 Y is larger, right? Now tell me, which one is larger? Y, right? Okay. And one more thing I want you all to know before this. I will maybe get back to this later. Okay. So do you guys agree that if let's say my binary is something like this, okay? This is my original binary number. If I take any one from it, okay? If I take any one from it, I make it into a zero. No matter what my right hand side is, this number is always going to be smaller. Can I say this? Even if this is 1, 1, 1, 1, 1, 1, 1, this number is going to be smaller than this number. Yes? Can I say this? Yes? Okay. Now, the second thing I want you all to know is, this is the first observation, okay? If you make a set bit 0, all elements to the right of it, all elements or all bits to the right of it can be anything. Okay. Now, the second thing I want you all to know is, bitwise OR never decreases, it always increases, only increases. Why? Because bits only get set. Let's say I've taken bitwise OR of some elements. Okay, let's say it's 1101. If I take the OR with 111, the OR bitwise OR becomes 1111. The bitwise OR never decreases. Okay, it only increases. So first thing is, if you make a set bit 0, all elements to the right can be anything, and the bitwise OR only increases, right? Now, what are we told? We are told that we know some XORs, okay? We know XOR 1, XOR 2, XOR 3, so on and so forth, up to XOR k. And this has to be smaller than equal to x. Okay. What does this mean? This means that let x be something in binary. If we take the OR of it, right? Either it is this, okay? Either it is this, or what is this? This OR of XORs is less than x. What does less than x mean? You take one of the bits, you make it into a 0. The right part can be as it is, okay? The right part is as it is, and the left part is as it is, and the right part can be anything. Does it make sense? Okay. Now, how do we go about solving this question? Okay. Like, we know that there are some XORs, XOR 1, XOR 2, XOR 3, XOR k. We know that we have to take ORs. We know that OR never decreases, OR only increases. Okay. And we know that the OR has this property. Either it is equal to this, or there is some element such that some bit such that it is 0. The left part is as it is. Okay. And the right part is and can be anything. This can be anything. Is this much clear? Is this property of the OR of XORs clear? Tell me, guys. Is this much property clear? Shaurya says yes. What about that? Okay. Now, Kashi says little bit. Okay, let me repeat. For a number to be smaller than any other number, okay, what basically happens is one of the bits, okay, the largest any of the bits, you can make it into a 0. Let's say all others are as it is, okay. If it is a 1, it's a 1. If it's a 0, it's a 0. To the right hand side, no matter what number you keep, this number is now always going to be smaller than this number. Why is this? Because 2 raised to x is greater than summation I is equal to 0 to x minus 1, 2 raised to I. Okay. This is a fact. What I'm trying to say is 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 is smaller than 2 raised to 3. And we know that the OR doesn't decrease. So the bitwise OR of whatever we are trying to find, okay, it's either x itself or it is x, but one of the bits is made 0, and then the rest is whatever we don't care about. Okay. Does this much make sense? Okay. Now, what are we trying to do in this problem? We are trying to fix this particular 0. Okay. For example, let's say x is something like this, right? Now, what possible ORs are there? Either the first element you make 0 and the next 6 elements you can keep anything. It doesn't matter. Otherwise, you make the second element 0 and whatever is to the right, it doesn't matter, right? We have 4 things. Or wait, we have 5. Or you make this bit 0. When you make this bit 0, it becomes 1, 1, 0, 0. And then there are 3 things to the right. Okay. Or you can make this 0. And when you make this 0, what happens? 1, 1, 0, 1, 0. And then whatever is to the right, it doesn't matter. Is this much clear? Basically, whatever OR we find, it is going to be of these types. I am not keeping them as 1, right? Even if they are 0. I am telling what happens when I keep this as 0. Then this is 0. Everything to the right doesn't matter. What if this becomes 0? Then where it is 1, I will put a 1. Then I'll put a 0 and so on and so forth. What if I make this 0? Then 1, 1, 0, I copy as it is. I make this into a 0 and whatever is to the right doesn't matter. And what if I make this into a 0? This I copy as it is here. I make this into a 0 and then the next two matters doesn't matter, right? Is this much clear? Tell me, Raj. Yes.
Hello.
Yeah.
So what I'm saying is, Gaurish, even if we don't make the MSBs, like even if we make them 0, why do we have to keep them 1? Like even if I set the MSB as 0, the answer will be less than X, no? The
Yes,
XOR.
yes. I am just telling you that we can fix which bit we want to set. You are right. If I set the MSB as 0, then this number will always be smaller than X. But do you also get that if I set this bit as 0, then also this number is always going to be smaller than X. And let's say I set this set bit as 0. Again, whatever number I create is going to be smaller than X. And let's say I put this bit as 0. Then also the number which I take is always going to be smaller than X. Is what I'm trying to tell you. Is this much clear, Raj? Like you took the MSB 0, but there can be other cases as well, right? Where the MSB is 1, but some other set bit is 0. Tell me. Yes. So these are, and now can you also say that, okay, now you say that these are all small parts and one last part, okay? This is just 1, 1, 0, 1, 1, 0, 0. Basically, when the OR is equal to X. Can you say that this covers all possible ORs? Because this covered all types of ORs that were possible, right? This one could be a 0. And whatever is to the right, it doesn't matter, right? I took all possibilities when this is 0. After that, I say, okay, no, this one is 0. This one is set. So I make this 0 and whatever is to the right doesn't matter. Basically, all possibilities containing this prefix. Then this prefix and this prefix. Do you guys intuitively understand that this considered all possible ORs? Because we are going through each prefix, we are fixing that prefix. Can you tell
Bhaiya,
me, guys? Yeah.
Bhaiya, can you use a small pointer for your pen?
Yeah.
We are unable to see what you are pointing there.
Okay. I was not pointing to anything, but let's say what I'm trying to say is I fixed one prefix, okay? I fixed another prefix, I fixed another prefix, and I fixed another prefix. What I'm doing is I'm fixing the prefixes, I'm making one of the bits to be 0, and whatever is to the right doesn't matter. In this process, do you see that I covered all possible ORs? Basically, here, whatever is there doesn't matter, right? Here, whatever is there doesn't matter. So in all these cases, all possible ORs are covered. Take a moment to understand this. Yes, clear? Okay. Now, this is all that we have to do. We have to fix what prefix OR we want. Okay. What do we have to do? We have to fix what prefix or we want, because we are covering all possible ors. Okay, so we are just fixing what prefix or we want. Let's say the array is 1 1 0 1 1 0 0. So we can first fix. What if I fix? What if I don't fix this? What if it is of type 0 0 0 0? Then what is the answer? What if my OR is of type 0 1 0 1 1 0 0? No, sorry. What if my OR is of type 0 0 and whatever? Sorry, this will be 1. What if my OR is of type 1 1 0 0 and then whatever I? Basically, I'm fixing all the prefixes. Then wherever there is a set bit, I'm making it into a 0. And then I'm saying, what will be my answer if my OR is this? Does this make sense, guys? Tell me. Okay. So in my, I'll get to what is the solution. But okay, for every bit, okay, for every bit, I am calculating what the answer could be in a calc function. Okay. What does this mean? From I to 30, it means that I'm setting the ith bit to 0. And then if I set my ith bit to 0, then what is my answer? This is what my calc function does, right? Now, we are given some ZORs, okay? So we are given some array, right? And now, let's say we know what type of OR we want, right? This 1 1 0 0, okay? Let's say something like this already exists. What I'm trying to say is, we took a prefix of ZORs. Let's say the current ZOR is ZOR. Okay, the variable is ZOR. If it falls under this, what do I mean to say if it falls under this? Okay. If I want my OR to be of type 1 1 0 0 and whatever is ahead, whatever is here won't really matter. But whatever is here, okay, these four should be a subset of this. What I'm trying to say, if my first four elements is this and I have anything, can I say that when I OR it with this, I'm going to get the same OR? Tell me. Yes. Now, if this is the OR, can I say I'm going to get the same OR? Yes. But in this case, can I say that I'm going to get the same OR when I OR it with this? No. Why? Because this and this is not the same. So when I OR it with this, I'm going to get a greater OR. So what I'm trying to say is, whatever this number is, it should be a subset of this. Like what is set should be given. It can be 1 1 0 0. It can be 1. It can be 1 0 0 0. It can be 0 1 0 0. Right? Or it can be 0 0 0 0. It can be only these four options. It cannot be 0 0 1 0, because when I OR it with this, it will become 1 1 1 0 and it will increase. We don't want that. So whatever current ZOR we have, it should be of this type. Does it make sense? Okay. Now, what does this mean? This means that if I have this particular mask, okay, 1 1 0 0, and let's say, what options did I have? Let's say I had 0 1 0 0 and I had, let's say, 0 0 1 0. These are two options. This one is possible, this one is not possible. Can you tell me, I want to check, okay, is this a subset of this, and is this a subset of this? Can you tell me what will happen if I take the bitwise AND of these two elements? I will get 0, 1, 0, 0, basically this number back. But what will happen if I take bitwise out of these two elements? I will get 0, 0, 0, 0. Can I say if I AND my, yes, I will teach you that also. I will teach you how to make that mask, right? Now, just bear with me. If you already have that mask and you know the current Zor's mask, if you AND it and you take and you get this, can you say that this is in the subset? Okay. And what was this? This was Zor of elements up to some value, up to some prefix. Yes or no, guys? Tell me. So what I'm trying to say is I iterated till, let's say here, the Zor of elements comes in the prefix of the OR that I want. Can I say that I can make a cut here? Basically, cut the subarray here. Tell me, guys. Yes, it is possible, right? Yeah. Shortest says yes. Okay. Yes. Kashish says don't know. The thing is, you can actually cut here. Why? I will tell you. Okay. Let's say you wanted 100, right? And the elements are 1000. The elements of the array, okay, 1000. The element again is 1000. And let's say it is 1010. Okay, and here it is again 1010. Right? Now, let's say this is the cut that is actually possible, right? Okay. And this is also a cut which is possible. Can you see if I cut here and the remaining is also a possible answer? If I take the OR of these two, it is still going to come in this particular subset. What I'm trying to tell you is, let's say it is 1000, and I'm not able to come up with a, let me try. This is a possible one, okay? Now let's say 0100 and 1000, and again 1000. Okay. Now this is a possible cut, and this is a possible cut. Now, if this is a possible cut, right? And the answer exists. What I'm implying to say is, you assume that the answer exists. Okay. Now, here, this is possible, and then this is also a possible answer, right? This is indeed a possible answer. But if you take this range and this range, it is also possible. And since we need to maximize, can you see that the first time I find that my Zor is smaller than equal to X, I can just make a cut. It won't really matter. and then again, when it is smaller than equal to, I can just make cuts. Does it make sense to you, Kashish? Yes. So what did we discuss? We discussed that we need to make cuts. Okay. And what do we do when we need to make cuts? We find the current XOR. Okay. And if the current XOR is of the type of prefix we want, what do? I make a cut. Is this much clear? Yes. Now, if I make a cut, I will just do the number of cuts I did plus plus. And in the return, what will I do? If I broke the entire array, I will return cuts. Otherwise, I will return n minus 1. Now, I will just find the maximum answer over all possible bits that I can make 0. And in the end, whatever is possible, right? What is the maximal possible answer? That is my final answer, because we are checking over all possible ORs. Does it make sense? Whoever is there in the post contest discussion till now. Okay. Now, how do we go about implementing it? Let's say you are given a binary number and you needed to find the mask of the first 4 bits. Okay. This is 2 raised to 0. This is 2 raised to 1. This is 2 raised to 2, 3, 4, 5, 6, 7. Tell me, what is 2 raised to 8? Isn't it 1, 0, 0, 0, 0, 0, 0? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, what is 2 raised to 8 minus 1? This is a very nice trick. Okay. What is 2 raised to 8 minus 1, guys? It is going to be 1, 1, 1, 1. 1, 1, 1, 1. Okay. Guys, what does mask mean? Mask means that I want to take a certain amount of elements, right? So I need a mask that picks it up. Think of it as I want to include a range, right? How do I include the range? I use something. What do I use? This thing is called a mask. Okay, it's called a bit mask. Okay. Yeah, I want this window, right? Now, I want the first 4 elements, right? Do you agree that this is 2 raised to whatever? So 2 raised to 8 minus 1 is going to give me all these set elements. So basically, if I do 2 raised to 30 minus 1, or I take int max, it is going to be this. Now I want, let's say, the first 4 elements, right? Do you guys agree that if I take this as my particular mask and I bitwise AND it here, since all of this is 1, whatever is here is going to come down and the rest is going to remain 0. Do you guys agree? Okay. So how do I get this mask? Because do you guys agree if I get this mask, everything is sorted? Put a yes in the chat if you guys agree. Like if I get this mask, whatever I wanted to check, I can check it. So, how did I come up with this instantly during the contest? I've practiced a lot of problems. So this trick is just intuitive to me, right? So I have 1, 1, 1, 1, 1, 1, 1, 1, whatever. And I want, let's say, only the first 4 element bits to be ones, right? Let's say this is I. What is 2 raised to I minus 1? Can you say it is 0, 0, 0, 0 till this? And then it is 1, 1, 1, 1, 1, 1, 1. Do you guys agree upon this? Yes. So if I just subtract this, Do you guys see that I get 1, 1, 1, 1, 0, 0, 0, 0, 0, 0? Tell me, guys. So this is how you get the bit mask. Okay. Now moving on to the implementation, the main part. If this is Mohan says once again, please. Mohan, so see, we wanted to extract the first 4 bits. So first, we took whatever. Let's say this is the largest bit here is I. So I took 2 raised to I plus 1 minus 1. Okay. What will this give me? This will give me 1, 1, 1, 1, 1. Now I want the first 4 bits only. No. Let's say what I'm trying to say is I want till the ith bit. This is the 0th bit. This is the first bit. This is the second bit. Let's say I want till the second bit only. So what is 2 raised to 2 minus 1? This is nothing but 4 minus 1, which is 3. If I denote 3 in binary, it is 0, 0, 0, 0, 1, 1. Okay. If I subtract these two, I get 1, 1, 1, 1, 0, 0. Basically, the first 4 bits are 1, everything else is 0. Now, if I take the bitwise AND of these two elements, I get what I want, right? 1, 0, 1, 1, whatever. Let's say there was 1, 1 here. The bitwise AND gives 1, 0, 1, 1, which is the first 4 bits. And here it is 0, 0, right? So I got what I wanted. Does this make sense, Mohan? Okay. Great. Right? Can you tell me the simple test case where we are setting MSB as 1? This won't give the most optimal answer, Raj. Let me tell you why. Because the thing is, how are you proving this? You can't prove this that this is the optimal, right? I will share a test case after the PCD. Let me just think about it. I can prove it right now, but let me just finish this PCD, right? Yeah, something like this. So moving on to the implementation, if you have understood the solution till now, we are going to iterate through all bits and we are going to assume that we are setting this bit as 0. So everything to the right can be anything as we want. It doesn't really matter. And everything to the left, we want it to be a subset. Okay. So this is what my calc function does. The size is the number of subarrays I'm making. Last index is the last index that I broke off. Okay. Basically, if this is my array, and if I broke off till here, let's say this is index I, then my last index is going to be I. Basically, what I'm saying is till the end, if it is not possible, then my last index is going to be I. So it is very important that I can break till the end, or my I or last index is equal to n minus 1. Is this much clear? Tell me, guys. I'm keeping a track of where I'm cutting. Okay. So I have XOR and I have OR. I iterate through all the elements. XOR equal to AI. What is my mask? My mask is int max. Why? What is int max? Int max is 2 raised to 32 or 2 raised to 31 minus 1. And this is just 1, 1, 1, 1, 1, 1, 1, 1, 1 in binary. Now I subtract, as I told you, 2 raised to MSB plus 1 minus 1. Okay. What I am trying to say is we are going to keep this element as it is, and to the right, whatever it is, it doesn't matter. Okay. So I'm subtracting that value. Basically, if I want in the starting x zeros, then it is 2 raised to x minus 1. Okay. Why take LL? It is not necessary. I just took it because I was not sure if my solution works, but it does. Not necessary. Okay. Now, we want to make sure that the XOR is 0. So first of all, I want my whatever my this bit is, okay, it's not MSB, it is just called a bit. It has to be 0. So XOR and this whatever bit has to be 0, right? So this is where I'm checking that. The next thing I'm checking is XOR is smaller than equal to X. That is very important. And what I'm checking here is that I think this is not necessary, but fine. Mask and XOR. Okay. Basically, the first these elements of my XOR and the first elements of my OR, these two are the same. When will this be the same? We discussed it up here. Okay. Let me take you right here. I have this element. I have this element. If I AND these two elements, I should get this element in itself. What is this element? This is X XOR mask. Okay. We have our X. We have set the first few elements. So what is this? This is X and mask. Is this much clear? X and mask gives me this value. Okay. Now what will give me this value? XOR and mask. XOR and mask is going to give me this value. Now I need to check, is ANDing these two elements give me this? So I have this, right? This is XOR and mask. Okay. How do I check if this is equal to the AND of this and this? I just put mask and XOR and X. So X and mask is my this element, and mask and XOR is my second element. So I don't need to write XOR 2 times. If I write it 1 time also, it is fine. So I'm just checking that mask and XOR is equal to mask and XOR and X. And this bit is 0. And XOR is smaller than equal to X. Then I just do OR times XOR. Basically, I'm ORing the current XOR with my XOR. I'm setting my XOR to 0. I'm doing size plus plus, and I'm setting my last index as I. Is this much clear? Tell me, guys. Kashish says yes. What about others? Okay. So here, what we are basically going to do is, in the end, since I am seeing where I'm breaking off, so I am just iterating over the last index. So if last index is not equal to n-1, basically stating that I didn't break the last subarray, or the bitwise OR is greater than X, then I return 0, basically stating that the cuts are not possible. Otherwise, I am returning the size. Is this much clear, guys? If it is not possible, then I return 0. When is it not possible? When the OR is greater than X, or the last index is not equal to n-1. Otherwise, I return size. And in the end, I print out the most largest possible size. Is this much clear? It's a very simple problem, right? So this was A, B, C, D. For E, I want to explain this problem, even though quite a few people will require this. The problem is so beautiful. And this is the problem that took me to master on Codeforces. This is what I want to teach you all, right? So the prerequisites for this problem, there are 2 prerequisites. One is combinatorics. Okay. And the second one is DP on trees. Okay. You are saying why is trees required when there is nothing about trees in this problem. And that is what makes this problem so beautiful. Like, I'm going to show you all why. Okay. So what is the problem? Some permutation of length n is guessed. You are given the indices of its prefix maximum and suffix maximum. Recall that a permutation of length k is an array of size k such that each integer occurs from 1 to k exactly once. Prefix maximums are elements such that maximums on the prefix ending are that element. More formally, the element AI is a prefix. Okay, whatever. Right? And suffix maximum, we are given this. We are told how many number of arrays are possible, right? Okay. Now, what are we given? We are told that there is a permutation of size n. What is a permutation of size n? It is an array where elements 1, 2, 3, 4 up to n occur exactly once. Okay. What I'm trying to say is 1, 2, 3 or 3, 1, 2 or 3, 2, 1. These all are permutations of size 3. Okay. Now, there, let's assume that such a permutation exists. Okay. 1, 2, 3. Okay. Now, we are given two arrays, prefix max and suffix max. The indices. I'll just write it down. This is 1, 2, 3, and this is going to be 3. What does this mean? This is the input. Okay. Prefix max input means that for all elements that are to the left of 1 are going to be smaller than it. Smaller than index 1. Okay. So here, all elements that are on the left are smaller than it. Okay. Simple. Now for index 2, all elements that are to the left of it are smaller than it. Okay. This also makes sense. And for prefix 3, all elements that are smaller than it are to the left. All elements that are left of it are smaller than it. Okay. Now, we are given a suffix array. Similarly, what does this mean? For index 3, okay, the third element, all elements to the right of it are smaller than it. This is what these two elements, these two arrays mean. So we are given n, we are given the indices where they are the prefix and suffix maximum, and we are told how many such arrays are possible. Such arrays are possible. Okay. Is the problem statement clear to you all? Okay. Okay. Now, if the problem statement is clear, let's take this example. Okay. 4, 2, 3 and 1, 2, 2, 3, 4. Okay. So what does this mean? This means that the size is 4. So there are going to be 4 elements. Index 1 is going to have a prefix max. Index 2 is prefix max. Suffix 2 is suffix max. Suffix 3 is also suffix max. Suffix 4 is also suffix max, right? So basically, this element has to be largest in this range. This element has to be largest in this range. This element has to be larger in this range. Similarly, this element has to be larger in this range, and this element has to be largest in this range. Does this make sense? Tell me, guys. Okay. Do you guys notice the first thing? the first element here and the last element here have to be equal, because this is nothing but the largest element or n itself, because nothing can be larger than n to the left of it and nothing can be larger than right to the right of it. So after 2 you cannot have any other prefix maximum, and before 2 you cannot have any suffix maximums. So these two indices have to be same, basically saying that this is where 4 comes. Okay, right. Suffix max, right? Maximum. Yeah, yeah. Now, what does this mean? This means that the second element is the largest element in the array. Do you guys agree? Do you guys agree, guys? Tell me, do you guys agree? Yes. Now, does this also mean that, first of all, 2 is going to be greater than 1 and 2 is going to be greater than 3? Yes or no? Yes. Okay. So 2 is greater than index 1 and 2 is greater than index 3. Similarly, can I say that whatever is at index 3 is going to be greater than index 4? Yes or no? Tell me. Since this is largest in this range, can I say this is going to be larger than this? Yes or no? Put a yes in the chat if you guys agree. Yes. So I will make this here. Now what I have created right here is a tree, okay? Where if you look at a node and if you look at its subtree, all elements in its subtree are smaller than, if you notice, and it satisfies these constraints. Basically 1, 2, 2, 3, 4. 2 has to be larger than 3 and 4. 2 is larger than 3 and 4. Okay. 2 has to be larger than 1. 2 is larger than 1. Okay. Similarly, 3 has to be larger than 4. 3 is larger than 4. Okay. Does this make sense? Okay. Now, tell me. Now we are going to build the array level by level. Okay. Now this is how I'm going to teach you how to apply DP on trees. Okay. 2, 1, 3, 4. Okay. DP on trees is not really necessary. I'm sharing the idea. I won't really go into much of depth, right? Because if you're really watching this and you want the solution, this much idea should be more than enough to get you to the solution. Okay. Now, let's say you wanted to build a permutation of size 1. How many possible ways are there? There is only one way, right? The array 1. Do you guys agree? Yes. So, for sizes 1, do you agree that the answer is 1? Yes. Always 1. Yes. Now, we need to build an array of size 2 such that, let's say this is index 3, this is index 4. Index 3 is greater than index 4. Do you guys agree for this also the answer is just 1? 2, 1, this is the answer that is possible. Right? Okay. So for this, 2, 1 is possible. Okay. For this, only the array 1 is possible. Right? Now, we need to compute for this particular subarray, right? Now tell me guys, this is 2, 1, right? But if I give you any distinct elements, let's say I give you 1000 and let's say 10, and I told you need to satisfy this condition, can't you just keep the elements like this such that you can satisfy the conditions? Tell me. Okay, so if I pick any two distinct elements here, can't I say that the number of ways I can make this is also the number of ways I can make that, I can make the array using those elements? Basically, using 1010, how many elements, how many arrays can you make here? Only one, right? 1010. Similarly, for let's say 10,001, how many arrays can you make? You can still make only one array. Okay. Now, for 2, 1, 3, 4, you know, for this you can make one. You can make, for this you can make one. Now, for this subtree, what is going to be the size of the array? First, tell me this. The size of the array is going to be 4. Yes. Okay. Also, we have fixed the largest element. So how many elements are we free to allocate? 3. Aviral says, can you re-explain how for 3, 4 you get 1? How for 3, 4 I get 1? Because this is the subtree, okay? What does this mean? That if this is index 3 and 4, whatever is at index 3 has to be larger than index 4. So if I put, let's say 2 and let's say I have the numbers 2 and 1, how many arrays can I make? I can make only one array, right? 2, 1. So given two distinct elements, how many arrays can you make? You can make one array. Now, getting back to the problem, you have fixed one element, so you can take 3. Do you guys agree that there is no relation between this subtree and this subtree? Like, there is nothing, there is no relation required between these two subtrees. Like, no element here has to be larger than any element here. It is not a requirement. They are not connected. Do you guys agree? Okay. So I have 3 elements and I have to give one element to this subtree, because to make this array here, I need one element, right? And here I need 2 elements. Can you tell me how many ways I can put one element here? 3. Basically, this is 3C1, right? I need to put one element here. I have 3. So the number of possible choices right now are 3C1. Yes or no? Yes. Now, the number of ways I can put an element here is, I chose one element here, okay? So the number of elements I have now is 2. So how many ways can I select 2 elements? 2C2. I have 2 elements and I have to choose 2. Does this make sense? Now I have 2C2. I have 2C2 combinations. And for each combination, how many arrays can I make? I can make one array here, right? Because I know I can make one array. Similarly, here for 3C1, how many arrays can I make? 1. So the final answer would be 1 into 3C1 into 1 into 2C2. Yes or no? Tell me. So this is all that we need to do. And because we are going to recompute some elements, I'm not going to specify what, like there is a lot of recomputation over and over. We use dynamic programming to just, yeah, DP it. Now, this is my combinations template. Basically, choose NK gives me NCR, okay? Right? So forget about this. I am making the tree here. Okay, one more observation. Let me just get back to this. For my prefix values, do you guys agree the first element is always going to be in my prefix max? Basically, there's nothing to the left of the prefix max, right? So in my prefix array, the number 1 should be there. Similarly, in my suffix array, the number n should be there. These two conditions should be there, yes or no? And these two elements have to be the same, yes or no? Yes? Great. So these are the necessary conditions for this array. So I'm printing this. If the first array element is not 1, or the suffix max last element is not n, or the first element's last element is not equal to the second array's first element, I print 0 because these are necessary conditions. Okay. Otherwise, what do? I make my tree. Okay. This is just code to make my tree. Basically, between two adjacent elements, I push back an edge. And for all the elements in between, I also push back an edge. Okay. Make sense? Yes or no, guys? Wait. Okay. Now, what do? I have a DP vector in which it is -1 and -1. Dot first, okay, in this, it's pair, right? So dot first is going to store the size of the subtree. Raj says, can you make, yeah, sure. Let me just explain how I make the tree. Let me take this example, okay? I'll show you how I make this tree. Let's take this 1 3 1 4 6. 1 3 1 4 6. Okay. So do you guys agree? No, 1 3 3 4 6, right? So first of all, do you guys agree that 3 has to be the root node? Okay. After this, 3 is larger than 1. So what I'm doing here is, I'll just show you the implementation. I go across my first array. I want to push back. In adjacency 3, I want to push back 1. So I'm pushing whatever is the next element. In that, I'm pushing the current element. Okay. This means that there is an edge between 3 and 1. Does this make sense? Okay. Now, another part is there is an element 2 which is not mentioned. Okay. Now the thing is 2 is smaller than 1 and smaller than 3. Basically, if 2 would have been greater than 1, whatever is here, okay, let this be x. If ARR 2 would have been greater than ARR 1, do you guys agree that ARR 2 would also come in prefix max? If ARR 2 would be greater than ARR 1, this is already the prefix max which is given. 2 is not mentioned. This means that ARR 2 is smaller than ARR 1. Yes or no? Yes? Tell me, guys. This condition should satisfy, no? So that is why I am iterating all the elements in between and I am pushing back. Basically, what I'm saying is the first element is going to be larger than the second element. Okay. So that is why I am making an edge over that as well. Kashish, if it's hard for you, it is okay. Like if you don't know about trees, this might be a little hard. Yes, yes. I pushed 2 to 1 in this case. Yes. Yes, 1 is the parent. Yes. 1 is the parent of 2. And 3 is the parent of 1. That is what I'm trying to imply. Does it make sense? Okay. I'm just giving you an idea how to solve the problem, right? After that, I do the same for the suffix array. I will just show you what we have to do. Okay. Let's say it's 1, 2, 3, and my prefix array is given as 1, 3. This means that this is the largest element in this range and this is the largest element in this range. Okay. Do you guys agree that this element right here has to be smaller than this element? Otherwise, this would have been maximum in this range, right? But it is not there in our prefix array. So there has to be an edge from here to here, and there has to be an edge from here to here. Does this much make sense? What about y'all? Does this much make sense? So I have 1, 3. So I'm going to make an edge between these two. This is ARRI and this is ARRI plus 1. Okay. So there is a edge between ARRI plus 1 and ARRI. After this, for all elements that are in between, they are going to be smaller than ARRI. So for all elements that are in between, there is going to be an edge from ARRI to that particular element. Does it make sense? So that is what I am implementing here, and I'm doing same for the other suffix array as well. Okay. Now, if dp node dot first is not equal to -1, return dp node. Basically, if dp is set, I return dp. Otherwise, the current size is 0 and the number of possible ways is 1. Okay. So first, I'm going to compute what is the size of my subtree right now, because that is going to be the size of the array I want to compute. Then, what did we discuss? We discussed that if I want to calculate for this, what is the answer? And I know what is the answer for this, and what is the size of this, what is the answer for this, what is the size of this, what is the size of this, and what is the answer for this. The answer is just, if it is n, and let me name this ABC, okay? Then it is just going to be, and I'm going to take 2, it is going to be NCA into X into N minus A CB into Y. This is going to be the answer for this node. Didn't we discuss that, guys? Yes or no? So that is all that we need to do. We know the current size. What is the size of the array? So the number of possible ways are 1, because initially 1. And what do I multiply it by? Math.choose whatever the current size is into NC and then R, right? So what will be R? The size of that child, right? What is the size of this child? So I am choosing DFS eyes first. I know what is the size, and I know what is the size of this particular node. What is dot second? Dot second will store the number of ways to make the array of that size. Dot first is size, dot second is answer. Okay. Now, so I just multiply this by mat.choose this, and I multiply it by DFS I dot second. What is DFS I dot second? It is the number of ways to make this array. Here it is X, right? So I multiply this by X. That is what I am doing. Why mod? Because the question asks that we have to print mod 1e9 plus 7. There are no negative values. The question asks that we have to print into 1e9 plus 7. So that is all that we do. And in the end, I have to store what I'm returning some value, right? So I'm memoizing here also. What is DP node and what are we returning? We're returning size and the answer. So I just make pair of size comma answer. And in the end, what do I print? I print DFS ARR1.back.second. Basically, I'm starting to make the array from the largest element. Basically, I'm calling the DFS function from the largest element. Then I'm going down recursively. I'm computing the answer for this, and then I'm computing the answer for this node. So ARR1.back is nothing but the largest element of the array. Basically, the last element of the prefix array is the largest element. So that is all that we have to do. Does it make sense, guys? Right. Let me explain it in DP sense. DP of I denotes number of ways to make array following conditions. This is the state, okay? Following conditions in subtree of I. This much is clear? Raj, put a yes in the chat if it is clear. Now, there are going to be some nodes. Let's say the size is A, number of ways is X, size is B, this is Y, size is C, this is Z. The number of nodes I can choose, let's say, is currently SZ. So, what is DP of I? DP of I is, of course, SZ plus 1 because that is size of the subtree. SZ is the number of nodes I can choose in the starting, right? So, plus 1 is going to be the size of the subtree, comma. Okay? The answer. What is the answer? First, how many nodes can I give here? I need to select A and I have SZ. So isn't this SZCA? Yes. And how many arrays I can make? I can make X arrays. Isn't this one thing? Okay. Now I have chosen A arrays. So the number of nodes I have is SZ minus A. Okay. So for this, how many choices do I have? I have SZ minus A, CB into Y. This multiplied by this. Okay. And now for the last one, I have SZ minus A minus B, C into Z. This is the answer for this node. And this is the transition. DP I dot second is nothing but the number of current nodes available, CA, for every child, okay, into its answer. Then you subtract whatever nodes you chose. Yes, final answer is DP root dot second. Yes, that is what I am printing. Yes, you are right, Raj. So this is the general idea of this problem. As you can see, I'm also subtracting the size as and when I'm going through. So this problem is very beautiful because, as you can see, there is nothing related to trees here, but you can visualize it in the form of a tree. Then you can apply DP on trees to find the answer, right? So all in all, a very pretty problem. And a small story about me. In TLE 2, I joined as a student, as a newbie, with a lot of hopes. And in the start of TLE 10 is the day I become master on Codeforces. So keep grinding. I hope all your dreams come true. So I hope you like the post-contest discussion. Thanks a lot for watching, guys. Let me stop sharing. Bye-bye.